On example 4, find dy dx for y equaling the quantity x squared plus 1 quantity cubed. So you can see that you have a function inside of another function inside of the cubing function. So if we want to take its derivative, it makes sense that we are going to use the chain rule on it. Now you could, if you wanted to, cube out this whole entire thing and then take it term by term, but the chain rule is going to speed up this process significantly. So the way that I write this then, dy dx is equal to, I am going to take the derivative of this exterior function. Exterior function, pretend like this is x to the third, okay? So you would leapfrog that power down 3 times, it's not really x, right? It's this interior part here, which is x squared plus 1 to the second power, right? So I just took the derivative of this cubing function with respect to the interior function there. Now we take and we have to multiply that times the derivative with respect to x of that interior function, which is the x squared plus 1. Okay, so I'm just going to rewrite some stuff. And now the derivative of that interior function is just a 2x, leapfrogging that thing down. And then just to make this look pretty, we might take this 2x and then multiply it times the 3 out front here and get 6x times x squared plus 1 squared. So you can bet that the thing that most people neglect to do with the chain rule is the chain rule component to it. It's the derivative of the interior. And if this is a multiple choice type of situation, you know, you can probably bet that that's going to be one of the answer choices. It would end it like right there, with people forgetting to multiply by the derivative of the interior. So this brings us to the general power rule, where y is equal to some function of x raised to the nth power. That's exactly what we had right here, some function of x raised to, in this case, the third power, where u is a differentiable function of x and n is some sort of rational number. Then we've got, in Leibniz notation, dy dx is equal to, and notice that what we just did is that we applied the power rule to it. We leapfrog the power down, take this power, leapfrog it down, and then subtract 1 from it, which is perfectly okay. But now you have to multiply it times the derivative of the interior function, du dx. Or if you prefer, in, let's say, that prime notation, d dx of u to the nth power is equal to, notice that the power just leapfrog down, subtract 1 from it, and then multiply that times the derivative of the interior function. All right, let's try this one more time here. On example, find the derivative of f of x is equal to 3x minus 2x squared, all raised to the third power. So once again, we have a function raised to a power. So I'm basically just applying this general power rule for functions, which is, you know, a consequence of the chain rule. So f prime of x is equal to, leapfrog this power down, 3 times 3x minus 2x squared. And then we need to multiply it times the derivative of the interior function here, which is, oh, whoa, what are you doing? You forgot to subtract 1 from the exponent, 2. Okay, there we go. Saved it. All right, now multiply it times the derivative of the interior function, which is 3 minus 4x. And you can call that a day. I mean, there's no kind of situation where I would say, hey, why don't you expand that thing out? Heck no, let's just leave it like that.